Homework 10, question 1. So the question is, from the lecture notes, collect the definition and the simple properties of examples of stochastic examples. So the first one, the Parsons process. So the there are three properties of Parsons process. The first one is the number of n t1, t2 of the points ti in the interval of t1, t2 of length t equals t1, t2 minus t1 is a Parsons random variable with parameter lambda t. So you can write it the probability as p of n of t1, t2 equals to k is going to be equal to the e to the negative lambda t times lambda t to the k over k factorial. The second one is that in the interval of t1, t2, and t3, t4, which are non-overlapping with the random variable, and t1, t2, and t3, t4 are independent. And third one is that at the time moment of t, there is no more than just one Parsons point. So we can see, for an example, that's how the Parsons point process looks like. So the mean of expect value of Parsons process is going to be e equals to x of t is going to be equal to lambda t. The first order of probability mass is going to be equal to p x of t equals to k is equal to e to the negative lambda t times lambda t over k to the k over k factorial. The autocorrelation is going to be equal to r t1 t2 is equal to lambda squared t1 t2 plus lambda times the minimum of t1 and t2. Autocovariance is going to be equal to c of t1 t2 equal to lambda 2 t1 t2 plus lambda minimum times minimum of t1 t2 minus the lambda t1 times lambda t2 is going to be equal to the lambda of minimum of t1 t2. So the mean of the Parsons process is not a linear function of t. The longer time we'll wait for the expect value is going to be larger. Second one is that the Parsons increment process. Y of t is equal to x of t plus epsilon minus x of t over epsilon, which x of t is the Parsons process. So the first order mass is going to be equal to p y of t equal to n over epsilon is going to be equal to e to the negative lambda t times lambda epsilon to the n over n factorial. The expect value is going to be equal to lambda. The autocorrelation is going to be equal to lambda square 1 t1 minus t2 as absolute value is going to be equal than epsilon, and then lambda square plus lambda over epsilon minus lambda times t1 t2 absolute value of that and over lambda square when t1 t2's absolute value is smaller than epsilon, and autocovariance is going to be equal to c of t1 t2 is going to be equal to 0 when it's outside of the range, and is going to be equal to lambda over square minus the lambda times t1 minus t2 absolute value of that over epsilon squared, and which will give us a triangle shape. When epsilon is goes to infinity, goes to 0, the triangle will become an impulse with the area of lambda. 3, the point impulse process. So z of t is going to be equal to the derivative of x of t. As we can see, the mean of expect value of that is going to be equal to lambda. The autocorrelation is going to be equal to lambda squared plus lambda times the impulse function of the t1 minus t2, and then autocovariance is going to be equal to lambda times the impulse of t1 minus t2. So we can see that the process of point impulse process has that zero mean and autocorrelation equal to lambda times the impulse of t1 t2. So the input function would be just a Parsons impulse process, and the output will be a linear time invariant system with the impulse response. 4. Semi-random telegraph signal. So x of t is based on a Parsons points as well. So the x of t is going to be equal to 1, 1k is even in 0 of t, 0 and t, and it's going to be equal to -1, 1k is odd in 0 and t. So the first order probability mass is going to be equal to p of xt equals to 1 is equal to e to the negative lambda times e to the lambda t plus e to the negative lambda t over 2. And probability of xt equal to -1 is going to be equal to e to the negative lambda t times e to the lambda t minus e to the negative lambda t over 2. So the mean is going to be equal to e to the negative 2 lambda t. Autocorrelation is going to be equal to e to the negative 2 lambda times t1 minus t2's absolute value. And then the autocovariance is going to be equal to e to the negative 2 lambda times the absolute value of t1 minus t2 minus e to the negative 2 times the lambda times the t1 plus t2. And then for random telegraph signal y of t equal to ax of t. So we know the probability is going to be equal to 1/2. So the mean is going to be equal to 0. The autocorrelation is going to be equal to e to the negative 2 lambda times the absolute value of t1 minus t2. And autocovariance is going to be equal to e to the negative 2 lambda times the t1 minus t2. And we know since the probability of y equals to 1 is going to be equal to probability of y t equals to -1 is going to be equal to 1 over 2. So y of t is a strict sense stationary. And then we also can prove that because the expected value of it is going to be equal to a constant eta, so it is stationary as well. So for the random walk, it's going to be equal to p of x of t is equal to x of n t, and then is going to be equal to n times the 1 over 2n. And then for the Werner process, it's going to be equal to w of t is going to be equal to limit of x of t, where x of t is the random walk process. So the first order density function is going to be equal to f, and w and t is equal to 1 over square root of 2 lambda alpha t times e to the negative w squared over 2 alpha t. So the mean of expected value of the w of t is going to be equal to 0. And then we know the autocorrelation is going to be equal to the minimum of t1, t2 times alpha. And the autocovariance is going to be equal to minimum of t1 and t2 times alpha as well.